So I've noticed that my audio, it seems to be lower than other channels. So I'm gonna just jack up the microphone here. Hopefully that helps. It does seem like it can clip, but hopefully that's better. All right. So it is 1:30 my time. I have until about 3. So it's about an hour and a half. I guess I go 3, maybe 3:30 before I need to get ready for dinner tonight. So that should be more than enough time to get through this chapter. It is a short chapter. And I don't think the exercises are, there's only one exercise, but it is a write a program exercise. So maybe we just blast through the reading and then spend the rest of the time doing that exercise. I'm excited to read this chapter because while I've used iNotify and I have written, shell programs using it, I haven't really scratched the surface as far as how it's implemented. There's just a bunch of tools that I've used that utilize iNotify, so it'll be nice to get a better understanding of some of the API surface for iNotify, the kernel syscall surface. And yeah, I think this is one of the first chapters where I'm really going to learn a lot. So let's dive in. All right, monitoring file events. Some applications need to be able to monitor files or directories in order to determine whether events have occurred for the monitored object. For example, a graphical file manager needs to be able to determine when files are added or removed from the directory that is currently being displayed, or a daemon may want to monitor its configuration file in order to know when the file has been changed. Starting with kernel 2.6.13, that's interesting, monitoring its config file. Usually, a lot of the services that I've operated in the past, if you wanted to make changes to a config file, you would make the changes and then you would send a sig hup to the process, the main process of the service, and that would trigger it to reload its configuration. But yeah, I guess in this situation, the service would just be monitoring its config file and reloading itself. That's interesting. I'm not sure if that's great from operability of the software, because you really want to avoid situations where the config could be invalid. Like say you are making changes to config and you make a typo, you write it out, and now the process is pulling that in and having a parse error, or potentially airing out the service entirely, crashing the service because it has an invalid configuration, and all you were doing was typing something out and saving it real quick and just made a slight typo. So usually with services, I'll make the changes to the config files and then I'll run a config check on the file to make sure it parses, and then I'll send the sig hup. And so that, from an operations perspective, is preferable to the service reloading its config, especially if it does it in a very naive way. You're giving an explicit command to the servers, hey, now I want you to reload your config, versus it just doing it when there's a file change. Starting with kernel 2.6.13, Linux provides the iNotify mechanism, which allows an application to monitor file events. This chapter describes the use of iNotify. The iNotify mechanism replaces the older mechanism dnotify, which provided a subset of the functionality of iNotify. We describe dnotify briefly at the end of this chapter, focusing on why iNotify is better. The iNotify and dnotify mechanisms of Linux are Linux specific. A few other systems provide similar mechanisms. For example, the BSDs provide the KQ API. I've heard of KQ, but I don't think I've used it before. I think it's something that is used in event queues, maybe? I don't know. I don't have much experience with it other than seeing it mentioned a few times. A few libraries provide an API that is more abstract and portable than iNotify and denotify. The use of these libraries may be preferable to some applications. Some of these libraries employ iNotify or denotify on systems where they are available. Two such libraries are FAM, File Alteration Monitor, and Gaiman, which is like a GNOME project. I was listening to Andrew Kelly on a recent call he did for the Zig project, and he was talking about how file monitoring APIs are kind of like a mess, especially on Mac. I think he was talking about. Yeah, so doing something that's portable, I would imagine, is challenging. But in my case, I don't really care. I'm like Linux only now at this point. The key steps in the use of iNotify API are as follows. The application uses iNotify init to create an iNotify instance. This system call returns a file descriptor that is used to refer to the iNotify instance in later operations. So you say, hey, I want a init. If you look at the prototype, it's a void. Gives you back the file descriptor as an integer. Pretty simple. The application informs the kernel about, I wonder how many times you can call init per process. Can you just do it like probably arbitrary amount? All right. 2, the application informs the kernel about which files are of interest by using iNotify add watch. If we look at the prototype for that, takes in the initted file descriptor, the path to the thing you want to watch, and then a mask. Mask is probably the type of events that you're interested in. So we use that to add items to the watch list of the iNotify instance created in the previous step. Each watch item consists of a path name and associated bit mask. The bit mask specifies the set of events to be monitored for the path name and its function result. As its function result, iNotify add watch returns a watch descriptor. So now we're getting back a watch descriptor, which is used to refer to the watch and later operations. The iNotify RM watch system call performs the converse task, removing a watch that was previously added to an iNotify instance. In order to obtain event notifications, the application performs read operations on the iNotify file descriptor. Not the watch descriptor, the file descriptor of the iNotify. Each successful read returns one or more iNotify event structures, each containing information about an event that occurred. So this is where you would do a read and you would block. I guess the read syscall would block until there's an event available. Each successful read returns one of the iNotify event structures, each containing information about the event that occurred on one of the path names being watched via the iNotify instance. 4, when the application has finished monitoring, it closes the iNotify file descriptor. This automatically removes all watch items associated with the iNotified instance, so you don't have to remove them manually. Unless you want to remove them and add others. The iNotify mechanism can be used to monitor files or directories when monitoring a directory, which I've only recently used it to monitor directories, because if the file doesn't exist, this is a thing that I ran into. If the file doesn't exist, you can't monitor it. So if you're trying to monitor for the creation of that specific file or symlink or whatever, or directory for that matter, you have to monitor its parent for those events, like the creation event. Okay. When monitoring a directory, the application will be informed about events for the directory itself and for files inside the directory. Exactly. The iNotify monitoring mechanism is not recursive. If an application wants to monitor events within an entire directory subtree, you must use inotify add watch calls for each directory in the tree. And then, of course, when you get updates where you add new directories, you have to then add new watches for them. A inotified file descriptor can be monitored using select poll epoll. Okay, so it can be done asynchronously, I guess. And since Linux 2625 signal-driven I/O, if events are available to be read. See, a lot of this stuff like select poll epoll, I want to just skip over to here and see where we're going to cover that stuff, because that stuff is like stuff that I don't know a lot of the API surface for. Threads. We got send file system call here. Alternative I/O models. That's where we're going to get into it. It's a second to last chapter where we talk about select and poll and epoll, p-select. This I'd be really interested in reading. All right, let's go back to where we're at. I think we're here. Yeah, it says right here, see chapter 63. An inotify file descriptor can be monitored using select, poll, epoll, and since Linux 2625 signal-driven I/O. If events are available to be read, then these interfaces indicate the inotify file descriptor is being readable. See chapter 63 for further details on these interfaces. The inotify mechanism is an optional Linux kernel component that is configured via the option config inotify and config inotify user. The inotify API. The inotify init system call creates a new inotify instance. See, we already went over all this. I don't know why I'm going to do that again. As its function result, inotify init returns a file descriptor. This file descriptor is a handle that is used to refer to the inotify instance in subsequent operations. Starting with kernel 2627, Linux supports a new non-standard system call inotify init1. This system call performs the same task as inotify init, but provides an additional argument, flags, that can be used to modify the behavior of the system call. Two flags are supported. The inclo exec flag causes the kernel to enable the close on exec flag for the new file descriptor. That's good. This flag is useful for the same reason as open close exec flag described in section 431. The in non-block flag causes the kernel to enable the O non-block flag on the underlying open file description, so that future reads will be non-blocking. This saves additional calls to fcntl to achieve the same result. So if you're doing non-blocking I/O, you probably want to set that up front. The inotify add watch system call either adds a new watch item or modifies an existing watch item in the watch list for the inotify instance referred to by the file descriptor FD. Makes sense. So we got these watch descriptors. They have paths and masks. The path name argument identifies the file for which the watch item is to be created or modified. The caller must have read permissions for this file. The file permission check is performed once at the time of inotified add watch call. As long as the watch item continues to exist, the caller will continue to receive file notifications even if the file permissions are later changed so that the caller no longer has read permission on the file. The mask argument is a bit mask that specifies the events to be monitored for path name. The mask argument is a bit mask that specifies the events to be monitored for the path name. We say more about the bit values that can be specified in the mask shortly. If path name has not previously been added to the watch list for the FD, then iNotify add watch creates a new watch item in the list and returns a new non-negative watch descriptor, which is used to refer to the watch item in later operations. This watch descriptor is unique for this iNotify instance. If path name has previously been added to the watch list for FD, then iNotify add watch modifies the mask of the existing watch item for path name and returns the watch descriptor for that item. This watch descriptor will be the same as that returned by the iNotify add watch call that initially added path name to the watch list. We say more about how the mask may be modified when we describe the in mask add flag in next section. Boop. The iNotified RM watch system call removes the watch item specified by WD from the iNotified instance referred to by the file descriptor FD. The WD argument is a watch descriptor returned by a previous call to iNotify add watch. Removing a watch causes an in ignore event to be generated for this watch descriptor. We say more about this event shortly. Okay, iNotify events. This is the good stuff. When we create or modify a watch using iNotify add watch, the mask bit mask argument identifies the events to be monitored for the given path name. The event bits that may be specified in mask are indicated in the in column of table 9.1. If we look at that, we have in, out, description, bit value. So these are not things that you can select for. So you can basically select for all these different things, and some of them come out this way. So these are the main ones. File is accessed, file metadata was changed, close write, file open for writing was closed, close no write, create, delete self, modify, move self, move from, move to, open. All events, move and close. Don't follow, don't reference symlinks. Mask add adds events to current watch mask for path name. One shot, monitor path name for just one event. Fail if path name is not a directory. And then ignored can come out of it. Is there overflow on event queue? It means there's a lot of events being generated. Unmount, file system containing object was unmounted. Boop. The meaning of most of the bits in table 19.1 are evident from their names. The following list clarifies a few details. The in attribute event occurs when file metadata such as permissions, ownership, link count, extended attributes, user ID, group ID is changed. The in delete self event occurs when an object, i.e. a file or directory, that is being monitored is deleted. The in delete event occurs when the monitor object is a directory and one of the files that it contains is deleted. The in move self event occurs when an object that is being monitored is renamed. The in moved from and in moved to events occur when an object is renamed within monitor directories. The former event occurs for the directory containing the old name, and the latter event occurs for the directory containing the new name. The in don't follow, in mask add, in one shot, and in only dir bits don't specify events to be monitored. Instead, they control the operation of the add watch call. In don't follow specifies that path name should not be dereferenced. If it is a symbolic link, this permits the application to monitor a symbolic link rather than the file to which it refers. If we perform an iNotify add watch call that specifies a path name that is already being watched via this iNotify file descriptor, then by default, the given mask is used to replace the current mask for this watch item. However, if in mask add is specified, then the current mask is instead modified by ORing it with the given mask, ORing it with the value given in mask. In one shot permits an application to monitor a path name for a single event. After that event, the watch item is automatically removed from the watch list. In only dir permits an application to monitor a path name only if it is a directory. If path name is not a directory, then iNotify add watch fails with the error e not dir. Using this flag prevents race conditions that could otherwise occur if we want to ensure that we are monitoring a directory. Reading iNotify events. Having registered items in the watch list, an application can determine which events have occurred by using read. To read events from the iNotify file descriptor, let's see. If no events have occurred so far, then read blocks until the event occurs, unless the open non-block status flag has been set for the file descriptor, in which case the read fails immediately with the error E again, if no events are available. After events have occurred, each read returns a buffer. See figure 19.2. Where's 19.2? Oh, it's on the next page here. Containing one or more structures of the following type. All right. I guess the read gives you back n. And then it's up to you to do the size of, but you got a char name here. It says a variable width on each struct. So how do you know the size of each struct? You just read to the character end, you hit the null byte, and then you go to the next struct. Maybe. So you get this iNotify event back. It has a WD, which is the watch descriptor. It has a mask. Oh no, it has a length inside there. Mask bits describing the event occurred. Cookie for related events for rename. Length is size of the name field, and then the name field. So you basically look at that size, the size of the struct and the size of the and the length field. You kind of add those together there to get the where you do like offset of plus the length to get the length of the entire struct, and then you would start your next struct after that. Yeah, here it is. So the length value includes the padding. Yeah, that makes sense. Sorry. So you got your watch descriptor, the mask, which is the type of event, a cookie, which relates multiple events, then the length, which then after this length is where the name is stored. It'll have a null turning byte and then optionally some padding here, and the length will include all the padding. So basically go to this offset, then you add the length, and then that's the next one. Go to the offset, add the length, that's the next one. Go to the offset, add the length, that's the next one. Alright, the WD field tells us the watch descriptor for which this event occurred. This field contains one of the values returned by the previous call to iNotify add watch. The WD field is used when an application is monitoring multiple files or directories via the same iNotify file descriptor. It provides the link that allows the application to determine a particular file or directory for which the event occurred. To do this, the application must maintain a bookkeeping data structure that relates watch descriptors to path names. So it doesn't actually have the path and the data that, okay. It's like, okay, it's on the application to keep that information. What is watch descriptor again? Is it an integer? Yeah. Yep. Alrighty. The mask field returns a bit mask that describes the event. The range of bits that can appear in the mask is indicated via the out column of table 19.1. Note the following additional details about specific bits. An ignored event is generated when a watch is removed. An ignored event is generated when a watch is removed. This can occur for two reasons. The application used an iNotify RM watch call to explicitly remove the watch, or the watch was implicitly removed by the kernel because the monitor object was deleted or the file system where it resides was unmounted. An ignore event is not generated when a watch that was established with one shot is automatically moved because an event was triggered. Okay. If the subject of the event is a directory, then in addition to some of other bits, the in is there bit will be set in mask. The in unmount event informs the application that the file system containing the monitored object has been unmounted. After this event, a further event containing the in ignored bit will be delivered. We describe the in queue overflow in section 19.5, which discusses limits on queued iNotify events. So far, this is a pretty clean API. Not a lot of complexity. I can see why there wasn't required to be a lot of writing about it, because it's pretty clean, to be honest. Alright, the cookie field is used to tie related events together. Currently, this field is used only when the file is renamed. When this happens, an in moved from event is generated for the directory from which the file is renamed, and then an in moved event is generated for the directory to which the file name is renamed. If a file is given a new name within the same directory, then both events occur in the same directory. These two events will have the same unique value in their cookie field, thus allowing the application to associate them. For all other types of events, the cookie field is set to 0. When an event occurs for a file within a monitored directory, the name field is used to return a null terminated string that identifies this file. If the event occurs for the monitored object itself, then the name field is unused, and the length field will contain 0. The length field indicates how many bytes are actually allocated for the name field. This field is necessary because there may be additional padding bytes between the end of the string stored in name and the start of the next iNotify event structure containing the buffer returned by read. It also means that you can get to the end of the struct without needing to read in the entire string for the path, which is a bit of a performance improvement. I forgot where I left off here. Let's just start at the beginning here again. The length field indicates how many bytes are actually allocated. For the name field, this field is necessary because there are additional padding bytes between the end of the string stored in name and the start of the next identified event structure contained in the buffer returned by read. The length of an individual identified event is thus size of the struct plus the length. Yeah. Yep. If the buffer passed to read is too small to hold the next identify event structure, then read fails with the error E invalid to warn the application of this fact. In kernels before 2.6.12, read returns 0 for this case. The change to use of an E invalid error provides a clear indication that a programming error has been made. The application could respond by performing another read with a larger buffer. However, the problem can be avoided altogether by ensuring that the buffer is always large enough to hold at least one event. The buffer given to read should be at least size of struct identify event plus name max plus 1 bytes, where name max is the maximum length of file name plus 1 for the null terminating byte. And then there might be padding too. You're forgetting about the padding, bro. Using a larger buffer size than the minimum allows an application to effectively retrieve multiple events within a single read. A read from an inotified file descriptor reads the maximum number of events that are available and the number of events that will fit in the supplied buffer. The call ioctl fdf ion read num bytes returns the number of bytes that are currently available to read from the inotified instance referred to by the file descriptor. I think that's the first ioctl call we've actually covered in the book, which is amazing. I might be wrong in that, but seems like it. We haven't dived into ioctl that much in the book yet. The events read from an inotified file descriptor form an ordered queue. Thus, for example, it is guaranteed that when a file is renamed, the in move from event will be read before the in move to event. Boop. Okay. Excuse me. All right. When appending a new event to the end of the event queue, the kernel will coalesce that event with the event at the tail of the queue so that the new event is not in fact queued. Huh? Let me reread that. If the two events have the same value for WD, mask, cookie, and name. So it basically deduplicates events. This is done because many applications don't need to know about repeated instances of the same event, and dropping the excess events reduces the amount of kernel memory required for the event queue. However, this means we can't use inotify to reliably determine how many times or how often a recurrent event occurs. All right. Example program. Although there is a lot of detail in the preceding description, the inotify API is actually quite simple to use. Listing 19.1 demonstrates the use of inotify. I mean, I totally agree with them. It seems very simple. So we include sys inotify limits, I guess, for the max of the path, or max name max or whatever it is, that constant. And then of course is helpers. And then we have display inotify events. We have main. So we can start up here just by understanding display inotify event takes in the event itself or pointing to it, and basically does some printing of all the bits of information. So it's just a printing, it's a printing of the event. So we define our buffer length to be 10 times the size of a struct that inotify plus name max plus 1. This is the formula he gave in the book, and I'm wondering, because he talked about the padding So this size of the iNotify event plus the name max plus 1. So that's like the size of the structure takes you to here. So these 4 fields plus the maximum of the name plus 1, but he doesn't take in consideration the potential padding needed here, because it's not going to pack multiple. I mean, I guess that might get you 1, and you don't need to worry about padding if it's just 1 element. But if you have more than 1 element, you're going to have that padding. And he has 10 here in his allocation. So if you actually wanted to have conceivably 10, 10 buckets for potentially the name max, then I think you would need to consider the padding. But also, like, you don't necessarily need 10. Like, it's probably great to just have 9. Like, you're not, semantically, it's not a big deal. All right, and you can always, I think you can always fit 1 in, because I don't think the padding matters on 1 element. Yeah, okay. All right, so we declare an int, which is the iNotify file descriptor, the watch descriptor, and then just this j for the loop down here. We then allocate our buffer, and we declare how many bytes we read for the read operation here. And then we declare a char p, which I'm not sure exactly what, that's probably path, but we'll see. And then the actual event itself. And then we just do some argc stuff, and then argc argv, and then we init to get back our file descriptor. We then go through a loop, and we say we want to watch on the file descriptor every argv j, and j starts at 1. So every path that we have on the command line for this program is going to get added as a watch. We want to see all events. And then we just print out, hey, we're going to watch this path for you. And then forever, we're going to read off of the file descriptor into the buffer, and we're going to say, hey, here's the length of the buffer. It's giving us back numRead. If it's 0, then we fatal. If it's -1, then we exit. And then we print out that we got some bytes from iNotify. And then we go, this p now, this char star is the pointer into the buffer. So we say, hey, the buffer is now p. So we're going to be mutating p, but we're going to keep buffer just pointing at the same thing. And then we say if the p is less than the buffer plus the number that we've read, then we can continue. But if p ever gets greater than or equal to the buffer plus the number we read, we've finished reading. And then we cast the pointer to an event, and then we display it, and then we compute where p should move to next, which is the size of the event plus the length, which we talked about before. And then that's it. Pretty straightforward program. The programming listing, get it over here. The programming listing 19.1 performs the following steps, so we're going to go over this again. Use iNotify init to create an iNotify file descriptor. Use iNotify add watch to add a watch item for each of the file names in the command line argument for the program. Each watch item watches for all possible events. Execute an infinite loop that reads a buffer of events from the iNotified file descriptor, calls the display iNotify event function to display the contents of each iNotify event structure within that buffer. The following shell session demonstrates the use of the program in listing 19.1. We start an instance of the program that runs in the background monitoring 2 directories. Okay, so we say, hey, dir1, dir2 in the current working directory. We then create commands that generate events in the 2 directories. We begin by creating a file using cat. So dir1 and dir2 already exist. That's important to note, because you can't watch things that don't exist yet. We then cat into a new file AAA, and we see that we got an increate and a iNotify create and iNotify open. The above output produced by the background program shows that read fetched a buffer containing 2 events. We continue by typing some input for the file and then the terminal end of file character. Oh, because cat is reading from standard in. Gotcha. So we say hello world, and then we type the end of file character. And then it says, hey, okay, we got a modify event this time. And with the end of file, we get a close right. We then read the file into another monitor directory. This results in 2 events, one for the directory from which the file moves, and the other for destination directory. So then we say move from dir1 to dir2 from A to B, and we get a move from A and watch 1 to, and a move 2 for B and watch 2. Makes sense. These 2, and I didn't see the cookie. The cookie was 584, whereas above here there is no cookie. These 2 events share the same cookie value, allowing the application to link them. When we create a subdirectory under one of the monitor directories, the mask in the resulting event includes the isdir bit, indicating that the subject of the event is a directory. At this point, it is worth repeating that iNotify monitoring is not recursive. If the application wanted to monitor events in the newly created subdirectory, then it would need to issue a further iNotify add watch call specifying the path name of the subdirectory. Finally, we remove one of the monitor directories, say rmdir, and that issues on WD1 2 events. The first one is in delete self, and the last one is in ignored. The last event, in ignored, was generated to inform the application that the kernel has removed the watch item from the watch list. Queue limits and proc files. Queuing iNotify events requires kernel memory. For this reason, the kernel places various limits on the operation of the iNotify mechanism. The superuser can configure these limits via 3 files in the directory proc sys fs iNotify. Max queued events. When iNotify init is called, this value is used to set up an upper limit on the number of events that can be queued. Hold on a second. Let's reread this. When iNotify init is called, this value is used to set an upper limit on the number of events that can be queued on the new iNotify instance. If this limit is reached, then an in-queue overflow event is generated and excess events are discarded. The WD field for the overflow event will have a value of -1. Max user instances. This is a limit on the number of iNotify instances that can be created per real user ID. Max user watches. This is the limit on the number of watch items that can be created per real user ID. Typical default values for these 3 files are 16,384, 128, and 8,192 respectively. Boop. An older system for monitoring file events, dnotify. Linux provides another mechanism for monitoring file events. The mechanism, known as dnotify, has been available since kernel 2.4, but has been made obsolete by iNotify. The dnotify mechanism suffers a number of limitations compared with iNotify. The dnotify mechanism provides notification of events by sending signals to the application. That's probably costly, because instead of doing just like a read, you're sending a signal which interrupts the process's normal execution to run the signal handler. And you have to like save off registers, and I mean, you're doing that for reading as well, because when you do a syscall, you have to save registers, but I don't know, it seems more costly to send a signal. Using signals as a notification mechanism complicates application design. It also makes the use of denotify within a library difficult, since the calling program might change the disposition of the notification signals. The iNotify mechanism doesn't use signals. The monitoring unit of denotify is a directory. The application is informed when an operation is performed on any file in that directory. By contrast, iNotify can be used to monitor directories or individual files, but they must exist. In order to monitor a directory, denotify requires the application to open a file descriptor for that directory. The use of file descriptors causes two problems. First, because it is busy, the file system containing the directory can't be unmounted. Second, because one file descriptor is required for each directory, an application can end up consuming a large number of file descriptors because iNotify doesn't use file descriptors. Well, it does use them, but not in the way that denotify does. It avoids these problems. The information provided by denotify about file events is less precise than that provided by iNotify. When a file is changed inside a monitored directory, denotify tells us that the event has occurred, but doesn't tell us which file was involved in the event. The application must determine this by caching information about the directory contents. Furthermore, iNotify provides more detailed information than denotify about the type of event that has occurred. In some circumstances, denotify doesn't provide reliable notification of file events. Further information about denotify can be found under the description of the fnotify operation in the fcntl manual page, and in the kernel source file documentation denotify. Summary. The Linux-specific iNotify mechanism allows an application to obtain notifications when events, files are opened, closed, created, deleted, modified, renamed, and so on occur for a set of monitor files and directories. The iNotify mechanism supersedes the older denotify mechanism. Exercise. So you got plenty of time here. Write a program that logs all file creations, deletions, and renames under the directory named in its command line argument. The program should monitor events in all of the subdirectories under the specified directory. To obtain a list of all these subdirectories, you will need to make use of nftw. When a new subdirectory is added under the tree or a directory is deleted, the set of monitored subdirectories should be updated accordingly. I guess we could do that one. Or we could continue on reading. I feel like I fully understand the API of iNotify now. It's very straightforward. I understand what it does. Like, I understand like how to implement this thing. It just kind of like, again, it's an exercise. There's nothing really super interesting there. Yeah, I'm gonna skip that exercise. It does sound interesting, but not interesting enough. So let's go ahead and move on to chapter 20 reading. And this is going to be signals. Finally. Fundamental concepts. Alright, that one's done. Get status, get add all. I didn't have any code for that. DC. And we'll say finish chapter 19. Boom. And then T, if I say T7 done, I am at almost 30% complete. Almost. we're getting up on close to a third of this book read. Wow. This has been quite the task just to get to chapter 20. Alright, let's check out this chapter here. So, we're starting on page 287, or sorry, 387. And we're going to page, there's a bunch of stuff on signals here. '87, yeah, 387 to 419. 419 minus 387. So that's about 32 pages. We have about an hour, so I think we can get through the reading in an hour. Let me go ahead and update the description on this video real quick to include signals. Boom. All right, chapter 20. Signals, fundamental concepts. This chapter and the next two chapters discuss signals. Although the fundamental concepts are simple, our discussion is quite lengthy. Since there are many details to cover, this chapter covers the following topics: the various different signals and their purpose is, the circumstances in which the kernel may generate a signal for a process, and the system calls that one process may use to send a signal to another process. So how kernel and user space send signals, how a process responds to a signal by default, and the means by which a process can change its response to a signal, in particular through the use of a signal handler, a programmer-defined function that is automatically invoked on receipt of a signal, the use of the process signal mask to block signals, and the associated notion of pending signals. I think when you apply the mask, they kind of get queued, or they're pending. The signal's pending, so when you remove the mask, I think the signal goes through, if I'm correct. It's been a while since I've done signal stuff. How a process can suspend execution and wait for the delivery of a signal. I think there's like a pause syscall I saw when I was like playing around with some things when I started reading this book. Man to pause. Yeah. I wanted to get that to work because I wanted to suspend the process, wait for the signal, and then resume the process. But yeah, I was having difficulty getting it to work. So that might be a program I implement as I read this chapter. Okay. Boop. Concepts and overview. A signal is a notification to a process that an event has occurred. Signals are sometimes described as software interrupts. Signals are analogous to hardware interrupts in that they interrupt the normal flow of execution of a program. In most cases, it is not possible to predict exactly when a signal will arrive. One process can, if it has suitable permissions, send a signal to another process. In this use, signals can be employed as a synchronization technique or even as a primitive form of interprocess communication. It is also possible for a process to send a signal to itself. However, the usual source of many signals sent to a process is the kernel. Among the types of events that cause the kernel to generate a signal for a process are the following. A hardware exception occurred, meaning that the hardware detected a fault condition that was notified to the kernel, which in turn sent a corresponding signal to the process concerned. Examples of hardware exceptions include executing a malformed machine language instruction, divided by 0, referencing a part of memory that is inaccessible. So sig seg v, sig divided by 0, and then invalid instructions. The user typed one of the terminal special characters that generates its signals. These characters include the interrupt character, usually control C, and the suspend character, usually control Z. I thought that was the shell that sent that signal, not the kernel. Obviously the shell is talking to the kernel to send the signal, but I think the origin of that is the shell, if I'm not mistaken, but perhaps I am. A software event occurred. For example, input became available on a file descriptor, the terminal window was resized, a timer went off, the process's CPU time limit was exceeded, or a child of this process terminated. Each signal is defined as a unique small integer, starting sequentially from 1. These integers are defined in signal.h, with symbolic names in the form of sig xxxx. Since the actual numbers used for each signal vary across implementations, it is actually some of them, like you see, like kill-9, like that is pretty universal, right? They're saying that sometimes kill-9 means different things on different versions of Unix or different implementations. That seems weird. It is these symbolic names that are always used in programs. For example, when the user types the interrupt character sigint, sig number 2, is delivered to a process. Signals fall into two broad categories. The first set constitutes the traditional or standard signals, which are used by the kernel to notify processes of events. On Linux, the standard signals are numbered from 1 to 31, so it's a standard. We describe the standard signals in this chapter. The other set of signals consists of the real-time signals, whose differences from standard signals are described in section 22.8. A signal is said to be generated by some event. Once generated, a signal is later delivered to a process, which then takes some action in response to the signal. Between the time it is generated and the time it is delivered, a signal is said to be pending. Normally, a pending signal is delivered to a process as soon as it is next scheduled to run, or immediately if the process is already running, e.g. the process sent a signal to itself. Sometimes, however, we need to ensure that a segment of code is not interrupted by the delivery of a signal. To do this, we can add a signal to the process's signal mask, a set of signals whose delivery is currently blocked. If a signal is generated while it is blocked, it remains pending until it is later unblocked, removed from the signal mask. Various system calls allow a process to add and remove signals from its signal mask. So that's what I was mentioning before. When you mask something, it kind of like puts it in the pending state and gets delivered after you remove it from the mask. But if I recall correctly, there are certain signals that you cannot mask. So if you use this as a mechanism to like ensure that your code is not interrupted, like when you enter a critical section of the code, I think there's certain signals that aren't maskable, so you might be interrupted still. So it's better to just make your code correct under the assumption that it might be interrupted at any time. In my perspective here. But again, I'm a novice systems programmer here. All right. Upon delivery of a signal, a process carries out one of the following default actions depending on the signal. The signal is ignored. That is, it is discarded by the kernel and has no effect on the process. The process never even knows that it occurred. The process is terminated, killed. This is sometimes referred to as abnormal process termination, as opposed to the normal process termination that occurs when a process terminates using exit. A core dump file is generated, and a process is terminated. A core dump file contains an image of the virtual memory of the process, which can be loaded into a debugger in order to inspect the state of the process at the time that it terminated. I think you can do a core dump and not terminate somehow, if I recall correctly. But yeah, maybe that's using some like ptrace magic or something. All right, the process is stopped. Executing the process is suspended. Execution of the process is resumed after previously being stopped. Instead of accepting the default for a particular signal, a program can change the action that occurs when the signal is delivered. It's known as setting the disposition of the signal. Wait a minute. Instead of accepting the default for a particular, so each signal has different defaults. A program can change the action that occurs when a signal is delivered. It's known as setting the disposition of a signal. A program can set one of the following dispositions for a signal. The default action should occur. This is useful to undo an early change to the disposition of a signal to something other than the default. The signal is ignored. This is useful for a signal whose default action would be to terminate the process. A signal handler is executed. A signal handler is a function written by the programmer that performs appropriate tasks in response to delivery of a signal. For example, this shell has a handler for the SIGINT signal generated by the interrupt character Control-C that causes it to stop what it is currently doing and return control to the main loop, so that the user is once more presented with a shell prompt, notifying the kernel that a handler function should be invoked is usually referred to as installing or establishing a signal handler. When a signal handler is invoked in response to the delivery of a signal, we say that the signal has been handled or is synonymously caught. Note that it isn't possible to set the disposition of a signal to terminate or dump core unless one of these is the default disposition of the signal. The nearest we can get to this is to install a handler for the signal that then calls either exit or abort. The abort function generates a SIGABORT signal for the process, which causes it to dump core and terminate. In Linux, the Linux-specific procpid status file contains various bitmask fields that can be inspected to determine a process's treatment of signals. Let's cat that out again. It's been a while since I looked at that. Cat proc self status. Let's see. These are all the signals here. As capabilities. Let's just grep for sig. I got 1, 2, 3, 4, 5, 6. Grep -I sig. Yeah. So I'm assuming pending, blocked, ignored, caught, and the queue. That's a big freaking queue. Obviously, it's not doing deduplication on those because like there's not that many possible values, right? Perhaps there is. I don't know. Okay, the Linux-specific prod pid status file contains various bitmask fields that can be inspected to determine a process's treatment of signals. The bitmasks are displayed as hexadecimal numbers with the least significant bit representing signal 1. Okay. Next bit to the left represents signal 2, and so on. These fields are sig pending, per thread pending signals, sketch pend, process wide pending signals. So we need to grab for that too. So we need to grab SHD E. I need to quote this bad boy and do a little thing like this. Boom. Okay, so the SHD pen process wide pending signals. So you got per thread pending signals, process wide pending signals, sig block, which is block signals, ignored signals, and caught signals. The difference between sig pen and SHD pen fields will become clear when we describe the handling of signals in multi-threaded processes in section 33.2. The same information can also be obtained using various options of the PS command. Boop. Okay. Signals appeared in very early Unix implementations, but have gone through some significant changes since their inception. In early implementations, signals could be lost, i.e. not delivered to the target process in certain circumstances. Furthermore, although facilities were provided to block delivery of signals while critical code was executed, in some circumstances blocking was not reliable. These problems were remedied in 4.2 BSD, which provided so-called reliable signals. One further BSD innovation was the addition of extra signals to support shell job control, which we describe in section 34.7. System V also added reliable semantics to signals, but employed a model incompatible with BSD. These incompatibilities were resolved only with the arrival of the POSIX 1990 standard, which adopted a specification for reliable signals, largely based on the BSD model. We consider the details of reliable and unreliable signals in section 227 and briefly describe the older BSD and System V signal APIs in section 2213. Reliable and unreliable signals. I remember hearing about unreliable signals at some point in my career. It might have been when I took this class with Michael Karisk, to be honest. But yeah, I don't really know much about the history there or why it would be useful today. Signal types and default actions. Earlier we mentioned that the standard signals are numbered from 1 to 31. On Linux, however, the Linux Signal 7 man page lists more than 31 signal names. Let's try pulling that up. Man signal. That is 3P. So we say man 7 signal. So 9 is consistent across all the architectures. I would hope so, because that's pretty common. SIG USR1, USR2, SIG SegV, segmentation violation. They just got to the end and like, that's SIG unused. Oh, they renamed it to SIG sys then. Signal types and default actions. You know, I think I'm gonna take a break here. It's been an hour, and I need to get ready at some point for dinner around 3:30, and I kind of want to just chill and relax for a little bit. Yeah, I'm gonna do that. So, just to kind of recap what we did today, we read the iNotify. We finished the directory stuff. We read the iNotify chapter and got partially into the signals chapter. I didn't do any coding exercises, but I did create a toy program to test out some concurrency stuff around the current working directory. Just to test to see if that is thread local or if it's process global, which is process global. It's stored in the kernel, but it's one per process, not one per thread or task. So yeah, that's a good amount of progress today, but I feel like I don't really want to continue on here at this point. So tomorrow morning I'll hop on and resume with signal types and default actions, and then we'll make, where are we at here? We're at 20. We'll make progress on signals. It's just going to be all signals this weekend probably, because I don't see myself getting all the way to the end of signals on Saturday. So we'll just crank on the signal stuff. Sounds good to me. All right, that's it for me today then. I will be back on tomorrow morning.